So thank you, Eric. So let me start by just explaining briefly the history of the coloring problem for graphs in general and for planar graphs in particular. So it all started with a question of Francis Guthrie in 1852. And Francis Guthrie, he wasn't a mathematician. He was doing geography, and he was coloring a map of England, and he was with the property that adjacent counties had different colors, and he was always, he could make that with 4 colors, and he was really wondering if this is true for every country or every map. So he asked the question to a relative who was a mathematician, and the question became some kind of hot question for mathematicians at this time, and it took some years until a proof by Kempe was found. So Kempe proved that you can always do that with 4 colors, but then it was found later that, that there was a flaw, there was a mistake in the proof by Hewood. But at least by fixing the flaw, it could be proved that you can always color every map with 5 colors, not 4, but 5. So this was just by correcting mistakes in the proof of Kempe. And then it took some 87 years until the new proof was given, and the proof turned out to be correct, not incorrect. And it was one of the first examples of a mathematical proof where computer is heavily used for verification. So I will try to give some ideas of how the proof goes, very vague ideas. And it's not the end of the story, because people in mathematics were a bit skeptic from the fact that a computer was used, and it was not clear that how human beings could check that. So was it really a proof? That wasn't completely clear. But 20 years later, Robertson, Seymour, and Thomas really simplified the proof. There was much less things to verify. A human being could really do that in a year, maybe. And so it was still a big improvement. And probably the end of the story is that Gontier and his team really gave the proof to Coq, the formal proof management system, though they wrote all the proof in Coq, and Coq said, OK, the proof is correct. So really, the Coq checked that no case was overlooked. Everything was fine. So I think it's pretty much the end of the story now, where you can argue maybe there's a problem with Coq. But if you ask Coq if Coq works, Coq said, yes, it works. So I guess it's fine. So it's self-verified. So, OK, so this is the question of Guthrie is really about coloring maps. So maps is not, well, a region or a country. It's not something very discrete. So we need to make it some discrete problem. So here's is a map. And to make it a discrete problem, you put a vertex inside every region. And now what you want, and you put an edge between 2 adjacent regions, you get a graph. And this graph has a nice property that edges do not cross. It's planar graph. And you color it. And then you assign the color of the vertex to the region, and you get the coloring as Francis Guthrie wanted. So really, now we are going to completely forget about maps and counties. We're only be talking about planar graphs and graphs on surfaces. So let me just tell exactly what the coloring is so that we are all on the same page. So given a graph G, a k coloring is an assignment of integers from 1 up to k to the vertices, such that adjacent vertices get different colors. And what you want to do is minimize the number of colors. So it's called the chromatic number, and it's denoted by chi of G. And OK, that's the chromatic number of a graph. What can we say about the chromatic number? I will just mention very basic results. First result is that checking whether the chromatic number of a graph is at most 2, it's easy. It does a very simple characterization. It's at most 2. The graph is 2 colorable if and only if it doesn't have an odd cycle. So clearly, If there is an odd cycle, then you can't color it with 2 colors, because if you try 1, 2, 1, 2, then you cannot find a color for this vertex. So if there is an odd cycle, you need at least 3 colors. But it's an if and only if. You can prove that if there is no odd cycle, then you can find a 2 coloring. And actually, this gives a polynomial time algorithm to check if a graph is 2 colorable. But as soon as you go to the next step, looking at deciding whether a graph is 3 colorable, things get hard. So deciding if a graph is 3 colorable, it's NP-complete, even if the input graph is planar, for which we know now that they're 4 colorable. So it's really a difficult problem. And yeah, as I told, we know from the 4-color theorem that planar graphs are 4 colorable. So these are some basic facts. A lot can be said in general about coloring, but I will just I will restrict myself to planar graphs and graphs on surfaces of higher genus. So before I give some explanations on how this can be proved, let me digress a little bit and explain how the 4-color theorem can be useful to prove some slightly more distant things. So take a planar cubic graph. So it's a planar graph in which all the vertices have degree 3. So I didn't draw the entire graph. I just drew some part of the graph. So all the vertices have degree 3. And it's a planar. And let's take it 2-edge connected. So I don't have something like this. Okay, this would be an edge whose removal disconnects the graph. And I don't have this. It's 2-edge connected. Okay. Let's do that. And if I have this graph, a nice thing is that when I take the dual, black graph, it's a triangulation. Okay? And since my graph is 2-edge connected, I don't have any loops. Because if there is such an edge here, when I look at the dual, I get a loop. Loops are not very good when it comes to coloring. Because when you color a graph, you want that for any endpoints of an edge, the 2 colors are different. But if you have a loop, it would mean that a vertex has a color different from itself. It's not possible. So we don't allow loops. Okay, so 2-edge connected, the dual is a triangulation. And from the 4-color theorem, I know I can color it with 4 colors. Let's color it with 4 colors. But instead of 1, 2, 3, 4, I'm going to use pairs of bits for some reason that will become clearer in a minute. So 0, 0, 0, 1, 1, 0, and 1, 1. Let's do that. It's a proper coloring. And now let us play the following game. I look at my original graph, and for every red edge, I look at the dual black edge, and I look at the 2 labels, say x and y, and I put as a label on the red edge the sum of the 2. And the sum is mod 2. So these are elements of, these are bits, if you want. So for any red edge, I look at the 2 endpoints of the dual edge, and I put the sum here. Let's do that. So this is what we get. So for instance, here 0, 1 plus 0, 0 is 0, 1. What can we take? 1, 0 plus 0, 0, and so on. You can do that for all edges. Let's have a look at what it gives. So there are 2 main observations. The first observation is that 0, 0 is never used, right? So why is it that 0, 0 is never used? So if I have 0, 0 here, it means that x is equal to y, because it's the sum mod 2. And it's not possible because it's a coloring. So you will never use 0, 0. So it really means that you are using only 3 possible labels, 0, 1, 1, 0, and 1, 1. This is the first observation. And the second observation is that around each vertex, the 3 labels that you see they're distinct. You never have 2 edges sharing a vertex with the same label. Why is it the case? Because assume that you did have a vertex and two edges with the same label. Well, in the dual graph, this corresponds to some triangle. And saying that these two labels are the same is the same as saying that these two labels are the same, because it's a sum mod 2. And this is not possible that these two are the same. They are adjacent. Okay? So the definition really implies that what I get is a coloring of the edges with 3 colors, such that around each vertex I see the 3 colors. So the 4-color theorem implies that when I take a cubic planar graph, I can color the edges with 3 colors, such that it's a proper edge coloring somehow. So it turns out that this is actually equivalent. You can prove the reverse statement in fairly the same way. I won't prove it. So actually, the 4-color theorem is completely equivalent to the following theorem. For any cubic planar graph that is two-edge connected, I can color the edges with 3 colors. And it's the same as saying that I can partition the edge set into 3 perfect matchings, right? Because around each vertex, you see the 3 colors. So each color class is a perfect matching. So if you're two-edge connected cubic planar, you have a partition of the edge set into 3 perfect matching. And it's equivalent to the 4-color theorem. And you see here that you cannot really forget this two-edge connected assumption, because there are two-edge connected cubic planar graphs. No, cubic planar graphs that are not two-edge connected, and they don't even have 1 perfect matching. So you have no hope to partition the edge set into 3 perfect matchings. Okay? So you really need this assumption. So these are 2 equivalent versions of the 4-color theorem. So yeah, let's finish this digression. I'm going to prove this extremely powerful theorem that planar graphs are 6-colorable. And it's not maybe, but it's not best possible, of course, but it's just to start with some ideas. So you remember Eulers' formula tells you that if you have n vertices, m edges, and f faces, the sum n minus m plus f is equal to 2. So if I give you a planar graph, a connected planar graph, let us assign some weight on the vertices and faces as follows. The weight of a vertex is its degree minus 6, and the weight of a face is 2 times its degree minus 6. So in a planar graph, I will consider planar graphs that don't have double edges, because when you color a graph, you don't care about double edges. You can remove them. So there are no loops, no double edges, so all faces have degree at least 3. So the weight of every face, since d is at least 3, it's always non-negative. So I put some weight on the vertices and faces, but the weight of faces is non-negative. So let us make the sum of all the weights. I claim that the sum of all the weights is exactly minus 12. Why is this? So if you sum this for all vertices, you get twice the number of edges, minus 6 times the number of vertices. And if you sum that for all faces, you get 4 times the number of edges, minus 6 times the number of faces. So if you look at Euler's formula, it gives you minus 12. Okay? This is not magical. Minus 12. So again, we put some weight on the vertices and faces, but all the weights of the faces are positive, non-negative, and you get a negative weight. So it means that one of these weights has to be negative, right? So it means that one of the vertices has degree at most 5. It's just a consequence of this. Well, there's other ways to get to this conclusion, but this specific way will be useful for us in a minute. So we proved that any connected planar graph has a vertex of degree at most 5, and it implies that every planar graph has a vertex of degree at most 5. Okay? So how do you deduce from this that every planar graph is 6-colorable? Well, you can prove that by induction. You take a planar graph, it has a vertex of degree at most 5, you remove it, you color your graph by induction, and when you add back your vertex, it has degree at most 5, so it has at most 5 colored neighbors. But if you have 6 colors, you will always be able to find a color that is different from all the colors of its neighbors, right? So once you know that there is a vertex of degree 5, you can use induction to color your planar graph. A non-inductive way would be to remove all the vertices of degree at most 5 one by one. This would give you an order of your graph, and then make a greedy coloring in the reverse order. So this, once you know that there is a vertex of small degree, inductively, this gives you a coloring. Okay, is this completely clear? Or, sorry if this is trivial for some of you, but so I won't give the proof of the four-color theorem, but what I wanted to do today is just to give you a taste of how you can use Eulers' formula to prove something slightly more involved than just there's a vertex of degree at most 5. Because the proof of the four-color theorem really tells you, okay, start with the Eulers' formula, and instead of just one vertex of degree 5, you would find one of hundreds of different configurations. And for each of these configurations, you would either inductively remove some vertices or contract some edges, find a coloring, and then find colors for the things that you have removed or contracted. This is how the proof goes. But to find one of these hundreds of configurations, you really need to work a little bit starting from Eulers' formula. And this is what we're going to do with a very simple example. So just to give you a taste of how it goes, we are going to prove this slightly more complicated statement. We proved before that there is always a vertex of degree at most 5. But instead, I'm going to show that there is a vertex of degree at most 4, or a vertex of degree 5 with a neighbor of degree at most 6. Okay? So these are the two possibilities. So a vertex of degree at most 4, or a vertex of degree 5 adjacent to a vertex of degree at most 6. Okay? So how do we do that? So we can assume that the graph is a planar triangulation. Because if you add edges to make it a triangulation, and you prove the result, and you find this, then the original graph also had one of these two configurations. So it's a planar triangulation. And let's do that by contradiction. Assume we don't have this. It means that there are no vertices of degree at most 4, so the minimum degree is at most 5. And you don't have vertices like this, so every vertex of degree 5, and I know that there are some, has all its neighbors of degree at least 7. Okay? So now we do the same as before. We put some weight on the vertices, d minus 6. And the total weight is still, I said at most minus 12, but the total weight is still exactly minus 12, sorry. Just as before, you make the sum, you look at Eulers' formula, it gives you that the weight is negative. So let's have a look at some numbers. So the minimum degree is 5. So we have the degree, and here we have the weight. So we have vertices of degree 5, 6, 7, and so on. The weight here is minus 1, 0, 1, 2, and so on. So we know that the total weight is negative, but the only vertices that have negative weight are the vertices of degree 5. And when you look at the vertex of degree 5, we know from our assumption that all its neighbors have degree at least 7. So they do have some charge. So this guy has minus 1, and all its neighbors have 1. So now the idea is that you must feel like Robin Hood, and you see that this poor vertex here has a negative amount of money on his bank account. But all its neighbors, they do have some money on their bank account. And you're very sad, and your moral principle tell you to make this situation even. You would be happy in a world where everybody would have a non-negative amount of money on his bank account. So how do you do that? Well, an easy solution would be for you to ask his kind neighbors to give it some money. So how much should he receive from each of its neighbors? So he has minus 1. If each of its neighbors give 1/5, then it's fine, because he has 5 neighbors. So let's make this rule. So it's not really Robin Hood anymore. It's more like a dictature. But every vertex of degree at least 7 gives 1/5 to each neighbor of degree 5. This is the general rule. Everybody does this. So now the vertices of degree 5, they're happy. They received 1/5 from each of their neighbors. They have 0 on their bank account. Maybe they're not so happy, but at least they're not indebted to the society. And the question now is what remains for the neighbors? We're not happy if these people are negative now. This is not what we want. We want everybody to be happy. So how do we analyze the charge that remains on these vertices that they gave some money? So let's look at the vertex of degree at least 7. How much did it give to its neighbors? Well, I claim that it can't give to 2 consecutive neighbors. Why? Because if it gave to these 2 neighbors, then these 2 neighbors have degree 5. And you don't have 2 adjacent vertices of degree 5 because all the neighbors of a vertex of degree 5, they have degree at least 7. So these 2, they're not adjacent. So you can't give to 2 consecutive neighbors. In fact, you can, in the worst case, you will give to only half of your neighbors because of that. So you start with d minus 6, you give 1/5 to at most half of your neighbors, you give at most d over 10. So the new charge, you can check that it's non-negative. So by this dictatorial rule, now it turns out that everybody has non-negative charge. But this is clearly a contradiction because, and this is quite sad, the contradiction is very sad. It tells you that not everybody can be happy. So the total charge is negative, and it's not possible that everybody has a non-negative charge. It's impossible. So we have a contradiction. Okay? So is this clear? So here we have 2 possible outcomes for our theorem, a vertex of degree at most 4, or a vertex of degree 5 with all neighbors, with a vertex adjacent to a vertex of degree at most 6. And we have 1 rule. This was the dictatorial rule. Well, in the 4-color theorem, instead of 2 possible outcomes, we have hundreds of them. And instead of 1 rule, there are dozens of rules. And this makes the analysis much more complicated. And this is why having a computer checking this is extremely convenient. And somewhat there has been a lot of progress recently on automizing this kind of proofs using linear programming. And people can now really, with the help of a computer, find all these rules and configuration in a much more efficient way as before, not by hand, but with the help of a computer. Okay, so I'm pretty much done for graphs, for planar graphs. I will maybe come back to that at the end. But do you have any questions so far before I move to graphs on general surfaces? Or okay. So we leave the plane for some time, and now we go to surfaces of higher genus. So it turns out that for surfaces of higher genus, the coloring problem is much easier. It was proved by Hewood in 1890 that if G is embeddable on the surface of Euler genus G, but not on the sphere, so Euler genus, is it clear what this is? The Euler genus is it's 2 minus the Euler characteristic. So it's the G such that this is the Euler genus. No, I take G. So for orientable surfaces, this is 2G. And for non-orientable surfaces, it's just G. Okay? So what can we say, and why is this true, and is it interesting, or is it sharp? So this is the question. So he would prove this. And interestingly, if you plug G equals 0 inside, so G equals 0, it's not really in the theorem, but let's put G equals 0, we get that chi is at most 1/2 of 8, chi is at most 4. So it turns out that because of the 4-color theorem, this is also correct for G equals 0. But the proof is very difficult. But if G is larger than 0, then the proof of this is extremely easy, and we will make it. Okay, this is quite interesting, that this somehow contains the 4-color theorem, but well, the proof is difficult. If I look at the torus, for instance, is G equals 2 because of this definition. So this gives me 48, 49. So the square root is 7. So I have 1/2 of 7 plus 7. I have 7. It tells me that I can color toroidal graph with 7 colors, and it's sharp. So let us prove this theorem. So the first remark is that we can assume that the embedding we consider is cellular. Why is this clear? Maybe I will not go into detail, but the formula that you want to show only depends on the genus. So if you want, you can consider a minimum genus embedding of your graph. And if you look at the minimum genus embedding, then if it's an orientable surface, then the minimum genus embedding is always cellular. And if it's a non-orientable surface, then you can always find a cellular embedding unless your graph is a tree. But if it's a tree, you can color it with 2 colors, and there's nothing to prove, really. So by this small technical analysis, you can really assume that your embedding is cellular. And you can assume that all the faces have degree at least 3. Again, you don't have double edges because you would remove them. They're not useful for you. So then you can apply Euler's formula exactly as before. So previously, it told us that when I sum all the degrees minus 6, I got minus 12. But now, because of Euler's formula, I get a 6G here. Before, it was negative, so I knew that there was a vertex of degree at most 5. But now it's not negative anymore, as soon as G is at least 2. So it's not true that there is a vertex of degree 5. But I can still say something about the minimum degree. Okay? So what can I say about the minimum degree? So let us divide everything by the number of vertices. So I get that the sum of the degrees minus 6 divided by number of vertices is at most 6G minus 12 divided by the number of vertices. But what is this quantity? So it's exactly the average degree minus 6. Is it what I want to show? Minus 6, yeah, exactly. So this is exactly the average degree minus 6. Because the sum of the degrees minus n is the average degree. So it tells me that the minimum degree is at most 6 plus this quantity. Okay? Just by the same analysis. So I know this. What can I say about the number of vertices n? Well, I claim that n cannot be too small. In fact, if you have a vertex of degree delta, and you certainly have a vertex of degree delta, then I claim that the number of vertices is at least delta plus 1. Well, if you have a vertex of degree delta, certainly you have delta neighbors. So in total, there are delta plus 1 vertices. And I don't double count vertices. You could claim, okay, but why is this vertex not the same as this vertex? We're on a surface, but there are no double edges, so this doesn't happen. So all these vertices are distinct, so I have at least delta plus 1 vertices. So I can replace this n by delta plus 1. And now when I multiply everything by delta plus 1, I get this second degree equation in delta, which I can solve. And this gives me exactly that delta is at most this quantity. Okay? So previously, in my planar graph, I was always finding a vertex of degree at most 5. And it was enough to, and it was enough to say that planar graphs were 6 colorable. So you only need to add 1 to get the chromatic number. Here I know that I always have a vertex of degree at most this quantity. So by the same reason, I know that the chromatic number is at most this plus 1. But it's exactly this value here. So we proved Hewood's formula. The natural question is it tight? It seems to be tight because for G equals 7, okay, it's tight. But is it tight in general? This is what Hewood asked. Hewood asked, is it tight in general? Can you do better? And in fact, it's very tight in the sense that for any surface, except the Klein bottle, you can embed the complete graph on this many vertices, the same amount of vertices, same number of vertices. And clearly, the size of the complete graph that you can embed on the surface is a lower bound on the chromatic number. Because if you have a complete graph on n vertices, then you need at least n colors. So this really tells you that the Hewood bound is extremely sharp. What shows this is a complete graph. It's not always the case that complete graphs are the most difficult to color on a surface, but in fact, it is the case now here. So the theorem of Ringel and Young, it's a series of maybe 10 papers in the 60s, and it's really extremely difficult constructions. And somehow it doesn't work for the Klein bottle. Why? So Klein bottle is G equals 2, and G equals 2 again. It gives 7 here, but you can prove that for the Klein bottle the chromatic number is at most 6 always, and you can really make a clique of size 6 on the surface. So it doesn't work for the Klein bottle for some reason, and it's not so difficult to prove. So it seems that it's pretty much the end of the story for coloring graphs and surfaces. You have this bound of Hewood. It's very easy to prove as soon as G is not 0, as soon as we're not on the sphere. And we have this deep theorem of Ringel and Young's that tells us that this is sharp. It's a bit strange. So when G is not 0, this is easy and this is hard. And when G is 0, this is hard. And this is very easy, that you can put K4 as a planar graph. Okay, it's not very difficult. This is K4. So it's really strange that there is this dichotomy between the sphere and the other surfaces. So is it the end of the story? Not really. And now I will come to things that Boyan talked about before the break. So this looks very specific, this kind of clique on this number of vertices. If you have a fixed surface and you take a random graph on this surface, very large random graph on the surface, typically you won't see this. Why? Because if you take a random graph on a fixed surface, a very large random graph, then the edge width of your graph will be very large. So it will not depend on G. It will only depend on the number of vertices. So if you take a very large graph, a typical graph on the surface will have very large edge width. So it won't contain a large clique. It won't even contain a large K5, actually. So a typical graph on a fixed surface doesn't contain this. So there's some hope that a typical graph on a surface, or more generally a graph with very large edge width, a locally planar graph, as Boyan called them just before, there's some hope that that coloring them is not as bad as this, that the bound you get would not depend on G, that will be closer from the planar case. And yeah, again, so this is what Boyan talked about this morning. A locally planar is a graph whose edge width, the minimum length of a non-contactable cycle, is extremely large, or large compared to G. And what Boyan mentioned this morning is that you can prove actually that locally planar graphs are 5 colorable. It's a result of Carsten Thomassen. And it really says that when you take a random graph on a fixed surface, then a large random graph that with probability 1, it's 5 colorable, so which is much more natural. Somehow, large graphs on surface typically behave like planar graphs in this sense. Well, not exactly like planar graphs, because planar graphs are 4 colorable, and here you only get 5. So what's the problem? Why can't you get 5 here? 4 instead of 5. And the reason is, well, there are many constructions, but there's a very nice construction of Fisk. So let me explain this. It's actually extremely simple and very, very nice. So what Fisk proved is that whenever you take a triangulation of a surface, any surface, such that all the vertices have even degree, at most 2 have odd degree, and these 2 vertices are adjacent, then you need at least 5 colors. So if you can find such a triangulation that is locally planar, then you're done. So let's first try to see why this is true, this result of Fisk. It's a very nice counting argument. So assume, for the sake of contradiction, that you have a triangulation like this, and it's 4 colorable. So you can color it with 1, 2, 3, and 4. And assume that the parity of faces colored 1, 2, 3 is some p. So p is either 0 or 1. We don't know. Okay? Let's look at the parity of the number of 1, 2, 3 faces. So what is a 1, 2, 3 face? It's just a face. It's a triangle colored 1, 2, 3. Okay? So let's do that. So the parity of 1, 2, 3 faces is of the number of 1, 2, 3 faces is p. What can you say about the parity of 1 to 4 faces? What can you say about that? Well, I claim that the parity is p also. Why is it the case? Because the sum of 1, 2, 3 faces and 1, 2, 4 faces is exactly 2 times the number of 1, 2 edges. Because whenever you have an edge 1, 2, this is 3 or 4, this is 3 or 4, and this edge contributes to the number of 1, 2, 3 faces and the number of 1, 2, 4 faces. So the sum of these 2 integers is even. It's 2 times the number of 1, 2 edges. Okay, the sum is even, so they have the same parity, actually. So you start with the parity of 1, 2, 3 edges, and it turns out that the parity of 1, 2, 4 edges is the same. But then it also means that the parity of 2, 3, 4 edges, 1, 3, 4 edges, 2, 3, 4 faces, 1, 3, 4 faces, and that's all. It's all the same. It's for the same reasons. All these things have parity p. Okay, is this clear, this argument? Yeah, you just it's twice the number of edges of each. So all these things have the same parity. It's quite nice. Now the question is, what's the parity of the number of say 1 faces? So it's a face that sees the color 1. What is the parity of this? Well, certainly the parity of this is the parity of the number of 1, 2, 3 faces, 1, 2, 4 faces, and 1, 3, 4 faces. Okay? So the parity is 3p. But 3p is just p. Okay? So the number of 1 faces, the parity is p. But you can do the same for all colors here. Not just one. Just any I face has parity p. But there's a second way to compute this. What is the number of I faces? Well, for each vertex colored I, the number of I faces, in fact, it's the degree of this vertex. Because for each vertex colored I, there will be the degree of this vertex, number of faces colored I. And all the other vertices, they're not colored I, so you don't double count things. So the parity of that is exactly the parity of the sum of the degrees of the vertices colored I. Okay? So we're almost done, because we have a graph in which all the vertices, except at most 2, they are even. So in particular, there are 2 colors that avoid the odd degree vertices. And so the sum of the degrees here is even. Okay? But saying that the sum of the degree is even is saying that P, that we were considering from the very beginning, P is actually 0. So we just proved that all that we have considered before, the number of 1, 2, 3 faces, 1, 2, 4 faces, all these faces, the number of I faces, all these things are even. But now, is it really possible that everything is even? Well, it's not possible. Because recall that you have 2 adjacent vertices of odd degree. The fact, so they have some colors, say 1, 2. But 1, the number of faces colored 1 is exactly the sum of the degrees of the vertices colored 1. And this is odd. And this is odd also, and we get a contradiction. All these things should be even, but now they are odd. This doesn't work. Is it clear, or? Yeah? So again, the idea is just to look, to verify that all the parities are the same, and then they are 0. But it doesn't go with the fact that these 2 things are adjacent. It would be possible if they were not adjacent. And if they were not adjacent, this would tell us that their 2 colors have to be the same. This is the only way you can make the parity of the sum of the degrees 0. But if they're adjacent, they can't have the same color, so it doesn't work. So this shows that whenever you find something like this, the chromatic number is at least 5. And actually, you can find things like this on any surface other than the sphere. Here is an example on the torus. So you have vertices of degree 6, vertices of degree 4, vertices of degree 8, and all the vertices of degree 4, 6, 8, except these 2 vertices here. They have degree 7, and they're adjacent. So it's a triangulation of the torus. All the vertices are even, except these 2, and these 2 are adjacent. So the chromatic number is at least 5. So there is really no hope to decrease this bound here. And this works on the torus, it works on any surface, actually, other than the sphere. So 5 is really the best you can do. And there's no hope to improve this in some way or the other. So I will not give the proof of this result of Thomason. It really uses the same ideas as what Boyan introduced this morning, planarizing collection of cycles, and we do some things. But it's a bit more involved. Maybe it doesn't fit this talk. So instead of this, I will prove a very similar result that is slightly easier to explain. So it's a result of Hutchinson. And it says that if you take a locally planar graph embeddable on a surface that is orientable, so before the result of Thomason works for orientable and non-orientable surfaces. Here, it only works for orientable surfaces, as we will see. So you take a graph embedded on SG with very large edge widths, and such that all the faces have even size. If you are a planar graph and all your faces are even, then you can be two-colored, because the faces they form a basis of the cycle. So if they're all even, all the cycles are even, and if all the cycles are even, as we saw, then the graph is two-colorable. So if you're in the plane, then you're two-colorable. But on any surface, it's not true anymore. But what Hutchinson showed is that you're not very far from being two-colorable. Actually, you're three-colorable. And first, we will prove this, because it will allow us to look at this planarizing collection of cycles and see some of the ideas of the proof. But before that, why doesn't it work on non-orientable surfaces? So it's only for orientable surfaces. The result, one of the reasons for that is this extremely surprising result of Young's. Young's proved that when you take a quadrangulation of the projective plane, quadrangulation all the faces of size 4, then the chromatic number is either 2 or 4. Either it's bipartite, the chromatic number is 2, or the chromatic number is equal to 4. It can't be 3. It's extremely strange when you see that. It's either 2 or 4. So there are several proofs of that. Proofs are the proofs are not very difficult, and actually it was found recently that you can also prove this theorem using topological methods like Bohr-Coulomb theorem in 2 dimensions. That when you have a 2-sphere that is covered by 3 opens or closed sets, then one of the sets contains 2 antipodal points, then this directly implies this bound. It's quite nice. But I won't go into details. So, and the point is that you can find such quadrangulation with very large edge widths, and this shows that you cannot prove this for non-orientable surfaces. So here is an example. On the left, you have a quadrangulation of the projective plane. It's not bipartite. And when you draw the corresponding graph, you get this graph. It's known as the Misielski graph, and it's a classical exercise for students to check that the chromatic number of this is 4, not 3. And you can make such things in a grid-like way that have very large edge widths, unbounded edge widths. Okay? So yeah, so it's embedded on a projective plane. So you have to identify antipodal vertices, and you obtain the graph on the right. Okay? So you have to identify this vertex and this vertex, this vertex and this vertex, and so on. So let us prove the result of Hutchinson. Not prove, but at least give ideas of the proof. So it's first we have to start with quadrangulation, because as Boyan mentioned, we are only considering edge widths here, whereas for this notion of planarizing cycle, you need the face widths. But if you're a triangulation or a quadrangulation, the two are not very far apart. And you can actually make sure that you're a quadrangulation without changing the edge widths by adding inside every face. So maybe you have very large faces. You cannot just put edges arbitrarily in the faces, because if you do that, you might decrease the edge widths. But what you can do is, inside every face, add this kind of thing. Well, maybe. If you add this kind of thing inside every large face, you get a super graph, and you can color this graph, and a coloring of this graph will be a coloring of the original graph. And now if you do that, it's really a quadrangulation, and you don't increase the edge widths by doing that. You don't, if maybe you can, if you add an edge like this, then you will decrease the edge width a lot if this is a large face. You don't want to do that. You rather do that, okay? So assume that it's a quadrangulation by adding this in every face of large edge widths. And what you can prove, exactly like you have the same kind of theorem. You have G cycles that are very far apart, and we'll see exactly what we mean by far in a minute, such that if we cut along each of them, we have a planar graph. And here, the difficulty of the proof is show that we can choose these cycles even. They all have even size. This is the difficult part. They're all even. They are far apart. And when we cut along each of them, what we obtain is a planar graph. So what do I mean by far? So far means, for us, it will mean the distance between two vertices is at least 4. You have at least 4 edges. And we need another condition that Boyan didn't talk this morning, but you can also prove that in a more general context. We want also that the distance between a cycle and itself is also quite large. So what do I mean by that? First of all, I mean that when I start at some vertex of a cycle and go to the left and then arrive to the right, I need this to be not too small, distance at least 3. So when I need that whenever I take a path between two vertices of a cycle, a path that is disjoint, internally disjoint from this cycle, I need that this path contains at least 3 edges. Is that clear? So it can either go like this, or maybe just go like this. Okay? Whenever I take 2 vertices on a cycle, I cannot find big shortcuts to this. I need at least 3 edges every time. So this is the technical condition of Hutchinson proof, but again, this is not so bad. The really bad thing is to make cycles even, and this is not quite clear. So remember that we start with a very strong condition. All faces have even size. But one thing that you can remark, if all faces have even size, if all faces have even size, there's one type of non-contractible cycles that are good for you. The surface separating cycles. I claim that if all faces have even size, this cycle is even. Why is it the case? Because if you cut along it, you have a new graph embedded on the surface, and this cycle is now a face of this graph. But this graph has all the faces are even. And this face has to be even by double counting, because the sum of the size of the faces is even. So if all the faces are even, this has to be an even face. So this has to be an even cycle. So in a graph like this, where all the faces are even, then all the surface separating cycles are even, the contractible and the non-contractible surface separating cycles. But then you can't really say much about non-separating cycles. Maybe they're odd. There's certainly some that are odd. But the difficulty is to take odd cycles and somehow combine them to make them even cycles with these properties. OK, how do we use this? So we will do as before. We cut along each of these cycles. So now every cycle becomes 2 cycles, actually 2 faces of our planar graph. And what I have is a planar graph. And it's a planar graph where all the faces are even. Because all the internal faces, they were even, and all the cycles we cut were even. So now all the faces of this planar graph, they're even. And as we saw, a planar graph where all the faces are even, it's bipartite. You can color it with 2 colors. Let's color it with 2 colors, red and blue. Well, there are some places where I'm quite happy because the 2 coloring of the cycles, they coincide. So I can really merge them again to make a coloring of my original graph. But there are some places where they don't coincide. They're just, they don't have the same orientation, if you want. And this is the case here, this is the case here. And here it's not clear how I should merge them again. So what do I do in this case? So let's consider 2 cycles like that. The first thing we do, again, we have 2 colors for the moment, red and blue, and what we want is to prove 3 colorable. So we have 1 more color to use. So let's recolor half of the vertices green, such that they really coincide. And now I only need to make this coincide. So let's color all the red. So first of all, is it bad to color all these vertices green, or is it OK? Well, I don't have shortcuts. I don't have chords here. So it's certainly not bad to put green things. I will not have an edge between these 2 things. And also cycles that are far apart. So this vertex will not interact with the vertex of another cycle. They're all far. So this is completely safe. Now I will recolor these red vertices blue. And this is not safe at all. Because, sorry, these vertices, they have blue neighbors. So it's certainly not safe to color them blue. But OK, let's recolor all these blue neighbors green. And I claim that this is completely safe. Because again, a path between 2 vertices here is quite large. So that I won't have an edge between 2 green vertices, either for some parity reason or for the fact that I don't have an edge between 2 green vertices. And I won't have an edge between a vertex here and a vertex close from another cycle, because then if I had an edge like this, it will mean that the two cycles are distance 3 apart, and there has to be a distance at least 4 apart. So really, I can do that in a safe way. And once this is done, I can really merge the two cycles again, and I get the 3 coloring of my graph on the surface. So this is how it goes, and this is not very far from the proof of Thomassen, that locally planar graphs are 5 colorable, but the cycles he has to consider are a bit more complicated. They have either even, or they contain some vertex of degree at most 4, or there's several conditions. But here it's fairly simple, but the ideas are very close. OK. So one thing I'd like to mention is that all these results on graphs that are locally planar, they have some consequences. They don't only tell you that if you take a typical graph on the surface, then they satisfy the condition. They also tell you that for any graph embeddable on a given surface, then if I remove constantly many vertices, then I get a graph with the right property. So assume my property is being 5 colorable. Thomassen proved that locally planar graphs are 5 colorable, and it implies that on any graph of Euler genus G, I can remove f of G vertices such that my graph is 5 colorable. And this is not difficult to see. You can prove that by induction. So if you have a graph of genus G, either the edge width is huge, and then your graph is locally planar, and it satisfies the property, or there is a short, non-contractible cycle. But if this is short, it has some size at most f prime of G, you can remove the vertices and apply induction. In each of these two parts, you can you can remove a constant number of vertices such that the graph satisfies the property. So this probably has to be some property that is closed under taking disjoint union, but for most properties, this would be OK. Or properties like coloring properties. So yeah, maybe I should say more about what P is, but for coloring properties, this works. So it really tells you that if you have a graph embedded on some surface, whatever the embedding, you can remove a constant number of vertices and take a 5 colorable graph. And interestingly, it's not known if this 5 can be improved to 4. So it's an old problem of Albertson. Albertson asked, can you always remove a constant number of vertices in a graph embedded on a given surface such that you obtain a 4 colorable graph? It's not known. And it's not even known for the torus. So in the torus, people believe that you can always remove 3 vertices and obtain a 4 colorable graph. But people don't know how to prove that. Let me add one more question before I go to a slightly different topic. So we've seen that planar graphs are 4 colorable, and an equivalent version of the 4-color theorem is to consider cubic planar graph and say that the edge set can be partitioned into 3 perfect matchings. And actually, the locally planar version of that is also an open question for some time. So it's not true that locally planar graphs are 4 colorable, but people think that the dual version is still true. So if you look at a 2-edge connected cubic graph embedded on some surface with very large edge widths, then it can be partitioned into 3 perfect matchings. That would be a very strong generalization of the 4-color theorem. It's not known if this is true. It's a nice question. So we talked about coloring planar graph earlier, and the only thing I showed you was there were 6 colorable, while the 4-color theorem tells you that there are 4 colorable. So you might be a bit angry at me because this is quite weak, right? You would like to see that there are at least 5 colorable. So let's do that now. And we will not see the classical proof. We will see a slightly different proof. And the point of this slightly different proof is that it doesn't use the Eulers formula. It doesn't use anything that we have seen before. It uses a completely different technique. So I think it's worth looking at this different proof strategy. We're not using discharging. You're not using configuration. We're using a completely different method. So let's prove that planar graphs are 5 colorable. And we're going to use a proof of Carsten Thomassen again. So what Thomassen proved is that if a graph is planar and you give each vertex some list of 5 colors, so every vertex has a different list of colors maybe, all the lists are completely arbitrary, then every vertex can choose a color from its list, so that what you obtain is a coloring. So adjacent vertices have different colors. In the coloring that we have seen before, we were always using the same list of colors on all the vertices, 1, 2, 3, 4, 5, 1 up to k. So in this slightly more general setting, you don't know anything about the list beforehand. You only know that you only know their size. You don't know what colors are in the list. So this is this implies that planar graphs are 5 colorable because you give every vertex the same list 1, 2, 3, 4, 5. Then Carsten Thomassen tells you that you can find a 5 coloring out of it. But this is much stronger actually. So how do we prove that? For the sake of induction, this will be by induction, we will prove a much more general statement. So the statement is that if I look at some graph, planar graph, if 2 specific vertices of the outer face have a list of color, a list of size 1, so it's the same as saying that you're given them some color, and you probably want the color here to be different, otherwise it's hopeless. If the lists have size 1, so they only have 1 unique color to choose from, and if all the other lists on the outer face have size 3, and if the lists inside have size 5, then you can find a coloring where each vertex takes a color from its list. So it's more general. You don't require 5 everywhere. You say 1 on these 2 vertices, 3 on the remaining vertices of the outer face, and 5 inside. So at first it seems completely crazy to do something as specific, but it turns out that each of these conditions is needed for the induction to work. So let's do the proof. So certainly it's true if the graph has size 3. Okay, maybe we should assume at the beginning that the graph we look at is a near triangulation. A near triangulation is just a triangulation. Every internal face has degree 3. All the faces except the outer face have degree 3 because you can always add edges inside of the graph, and if our result is true, then the result is true also for the original graph. So we can assume that all the faces, all the internal faces have degree 3. Wait.
Don't you mean 2 for first spider?
Sorry, 1 for 2 edges. Sorry?
Don't you mean 2 colors for each? Otherwise you just pick the same color for both.
No. So you have to assume that the 2 colors that they have are different.
Okay, but you can...
No, I didn't say that. So I said that in this very tiny difference here.
Sorry.
So no, this is a very good remark. So you have to assume, I didn't write it, you have to assume that the 2 colors that these 2 vertices receive, they're different. Otherwise, it's completely hopeless. Yeah. This is a good remark. So, but if this is true, then this works. So let's prove it. So we prove this by induction, and certainly if the graph is just a triangle, it's okay. Because if it's a triangle, then you have some color here A, some color B here. These are the list of size 1. And here you have 3 colors. Maybe the list is A, B, C, but you can always pick C here. And it works. So it works if it's a graph with 3 vertices, which is always good to know. Safe assumption. And what can we say in general? So the first remark is that I don't have this. This is the first remark. Why don't have this? Because if I had this, then my 2 pre-colored vertices, these 2 things, they have to be here or here. So let's assume that they are here. Maybe this vertex can be pre-colored. I remove this part. I apply induction. So this is really a graph where I have a list of size 5 inside, 3 here, and 1, 1. And I can color this graph by induction. OK? I color it by induction. So I really have a coloring of this graph. And this fixes this color. But now, here also, I have a list of size 3 here, some list of size 1 here, 5 here. So I can extend the coloring to the left-hand side, right? I can color the right-hand side by induction, and then extend it to the left-hand side also by induction. So I don't have a vertex like this, a cut vertex. But for the same reason, exactly, I don't have a chord on my outer face. Because for the same reasons, my 2 special vertices, they have to be somewhere. Here, maybe. So I could color this part by induction. And if I do that, this fixes these 2 colors. And then I can extend this to this part by induction also. Because these 2 colors are fixed, and this is exactly my statement. If I fix 2 colors, all the list of size 3 here and 5 here, it works. So really, these 2 specific vertices here, they're only here to make sure that when you consider a graph, the outer face is nice. You don't have cut vertices and you don't have chords. This is really their only purpose. OK? So we can assume that the graph, the outer face is nice. So we have a nice outer face. No chords, no cut vertices. And we have our specific vertices where the color is fixed because the list has size 1. So let's look at the next neighbor here on the outer face. It's a triangulation inside, so when I look at the neighbors, I really see something like this. And since I don't have chords, all these vertices here, they're really inside. They are not on the outer face. OK? So remember that this guy has a list of size 3. So say maybe A, B, C. And this guy has some fixed color. And maybe it's one of these. So assume, in the very bad case, maybe the color here is A. And I'm quite unhappy because I only have the choice of B and C for this guy. But OK, assume this is A. In this case, I remove A here. So the only 2 possible colors here now are just B and C. OK? So what I will do is I will completely remove this vertex, but I will also remove B and C from all these lists. Remember that inside, I had lists of size 5. And all these vertices are inside. They had lists of size 5. You remove 2 colors, B and C, B and C. Now their lists have size 3. So it is really the case that all the vertices on the outer face have a list of size 3 now. So you can apply induction. So apply induction, you color your graph. You can find a coloring from this list. And now the major point is try to extend this coloring to this vertex. And it's completely safe. I mean, from the point of view of these vertices, it's completely safe because these vertices, they don't have B and C in their list. So I can use B or C here, it doesn't matter. It will be different from all these colors. And why is it very good to have the choice between B and C? It's because I have no control on the color of this vertex. So this vertex has some color. Maybe B or C, but whatever, whether it's B or C, I can always choose between B and C here. So whatever happens, I will extend my coloring here to this vertex. And this is over. This proves the theorem. So again, when you see these things for the first time, it's extremely disturbing. But the pre-coloring argument is really there to prevent these kind of things from happening. And the two choices of like list of size 3 and 5 is really to make this extension possible. But it's a very, very neat argument. And the reason why I wanted to show you this is that it doesn't use any of the ideas that we have seen before, relying on Eulers' formula. It really uses a completely, I would say combinatorial, but graphic view of things, not topological at all. And this is really nice. And so it can be used to prove this kind of technique can be used, pre-coloring, extension, to prove many other results on graph coloring or coloring graphs and surfaces. And now what people try to do is really a combination of discharging technique and this kind of list technique. So yeah, I think it's the only thing I wanted to say. So I hope I wasn't too fast, but I think you will forgive me when you'll be in front of your lunch. So are there any questions first? Yes? Yes?
Just a comment for the remark you made for Hutchinson. So just a remark that if you take quadrangulation of projective plane, the surprise result is that it can never have chromatic number 3.
Yeah, but this is what I said, no?
No, you gave an example.
Yeah. But this is what I said. I said that it's a theorem of Young's.
Okay, I did not know. I thought you were just giving an example.
No, it's a theorem of Young's. It can only be 2 or 4.
No, it could be even higher. Oh no, like bigger surfaces could be higher. It can never be 3.
No, it's fine. Just to make it. So this is the theorem of Young's. Any non-bipartite quadrangulation has chromatic number equal to 4. Yes. Oh yeah, so that's a good question. Can you do the same thing with list of size 4, for instance? Yeah.
Maybe with another.
With another approach. So first of all, you cannot. So in the result of Carsten here, you cannot change the 5 to 4. So you can't really prove the 4-color theorem with this kind of technique. Well, it's not completely true, but if the same result with 5 replaced by 4 doesn't work. You have examples where planar graphs where every vertex has a specific list of size 4, but it doesn't work. So there are nice examples of void. It's a nice gadget, and it doesn't work. So people thought originally that this would be a good approach for the 4-color theorem, because what we see with this kind of approach is that having lists is extremely useful when it comes to doing induction. Because when you do induction, you color things, and maybe the lists get different. It's very useful. People thought at some point that it would be a useful approach for the 4-color theorem, but it turns out that pretty much at the same time as Carsten Thomas and Voigt found examples that show that doesn't work. But it's not completely true that this is hopeless approach to prove the 4-color theorem. And there's a conjecture that is open, and it has a least taste, and it's not known to be false for the moment. So the problem is that it's a conjecture of Kungen and Ramamurti. I hope I didn't spell things wrong. So the conjecture is that if G is planar, and every vertex has a list of 2 colors, an arbitrary list of 2 colors, then you can choose colors in each list. so that no odd cycle is monochromatic. So you don't have an odd cycle that is only of the same color. Okay, so take a planar graph, give each vertex a list of 2 colors, then you can find colors such that no odd cycle is monochromatic. And this applies the 4-color theorem. Because if you give every vertex the list 1, 2, and you find such a coloring, then then 1, there's no odd cycle colored 1, so 1 is bipartite. So you can color 1 with 1 prime and 1 second. And 2 is also bipartite, so you can color 2 with 2 prime and 2 second. So you can color your graph with 4 colors. But the original statement is pure list coloring in some sense. And not much is known about this conjecture. Thomassen proved that this holds if instead of odd cycle, you consider triangles. You can only prevent monochromatic triangles. But it's not so clear that it's true. I think it's quite difficult. So this is why I say that it's not list coloring is not a hopeless approach to find an easy proof of the 4-color theorem. Oui.
Do you know if this gives some algorithmic properties to, well, so this proves yeah, so these proofs, or for example, the discharging proofs, they show existence, but do they lead to algorithmic?
Yeah, they most always give quadratic algorithms.
Okay.
Because when you make discharging, so you put your weights, you make discharging. In the proof, I say, oh, we have a contradiction. But in reality, if you inspect the weight that remains on each vertex after the discharging, you know that it's negative. So you know that some vertex or some face will have negative charge, and you will find it if you apply the discharging rule in an algorithmic way. And once you find it, you will find an exact configuration that you like. So in our case, you would find a vertex of degree 4, or a vertex of degree 5 adjacent to a vertex of degree 6. So if you reapply the discharging algorithmically, and then check what thing is negative, and there has to be something negative, then you will find the configuration. And once you have found it, you can remove things, apply induction. So this is completely, this is exactly an algorithm, and usually it's quadratic algorithm.
Okay.
You can do the same in order to obtain the bound of Heawood?
Yeah, you can do, it's the same. Heawood bound you can obtain, but not without discharging. You can, I mean, you know that a small degree vertex exists, so you can find it. It's in very easily in linear time, a vertex of a certain degree. Just count the degrees. But for more complicated discharging, this also works. It gives a quadratic. The 4-color theorem is actually an algorithm, a quadratic algorithm. Quite complicated one. And all list coloring approaches are also purely algorithmic in some sense.
More questions?
You gave a theorem which connects surface of genus G and embedding of a complete graph on Heawood number of vertices. What is known in general about genus of complete graph?
So this is exactly what Ringel and Young said. That this is you can embed cliques of this size on this specific genus, and this is the best you can do.
The best.
It's really,
okay.
yeah, exactly. Yeah. But it's the best because of Heawood formula in some sense. The two results are dual one of another. If you could embed a larger clique, if you could embed a larger clique on the surface, then this would contradict Heawood's formula. because for a click on n vertices, you need at least n colors, right? So because of Heawood bound, you cannot embed a larger click. And because of Ringel and Young's, you cannot find a smaller click, and you can, I mean, it's, the two things are best possible somehow.
One more question, maybe? No?
Thank you.